My name's Tony Worth. I'm at the School of Computer Science here, University of Sydney. Very great pleasure to have Robert Tarjan with us. Before we begin our meeting, I'd like to acknowledge the traditional owners of Australia, recognise their continuing connection to land, water and culture. We're currently on the land of the Gadigal people of the Eora Nation, and we pay respects to their elders, past and present. As a university community, we're committed to learning from Indigenous knowledge systems and working together toward truth, justice and reconciliation. Professor Robert Tarjan is the James S. McDonnell Distinguished University Professor of Computer Science at Princeton University. Inter alia, he's won the inaugural Nevanlinna Prize from the International Mathematical Union, the Turing Award from the Association of Computing Machinery, and the Paris Kanellakis Award at Theory and Practice. When studying and researching computer science, it's heartwarming to know that some of those who founded the field are around us, are teaching us, are writing papers with us. I first encountered Professor Tarjan's work as an undergraduate. His name plastered all over the textbooks. In choosing where to apply for my PhD, his presence at Princeton was in no small part. I first encountered him in person as the instructor of Advanced Algorithm Design, COS 521, when I arrived at Princeton in September 2000. You can find the course outline link from my LinkedIn post about this seminar. Bob Tarjan was a legend in the classroom. Frequent references to Napster with his arm outstretched. Do you remember that? Tricky assignments based on recent research papers, left-handed, cowboy boots, purple shirts, occasional lectures where he was on the West Coast. We didn't have Zoom back in 2000. His phone number written on the board, amazingly, and regular mentions of his monograph. Bob let me chat with him about random topics. Who knows the nonsense I spouted? But he was patient and kind to a boy with an eagerness to theory and without a lot of background. Perhaps he saw himself as a father figure. Turns out that during his Stanford PhD days, one of his classmates, Richard Brent, had previously, as a high schooler, played chess against my father back in Melbourne. Professor Tarjan was on my oral exam panel in 2002 during my PhD. I've never seen my PhD advisor look so concerned. Would I fail him in front of this senior figure? Bob asked me a question about a postman that I think I got right. He hired me later to work with him at HP as an intern, and in my final year, he said he was likely to be away for my PhD defense and therefore wouldn't be on the panel. But he showed up anyway. But thankfully, he also paid me the compliment of showing up to my celebration that night at dinner. Thank you very much. Anyway, he's here at the University of Sydney, co-hosted between my school and the Sydney Mathematical Research Institute to discuss is Dijkstra's algorithm optimal. I give you the man of legend, Robert Tarjan.
Thank you. It's good. Thank you. It's great to be in Sydney. Second time I've been here. It's great to see so many eager young faces interested in something other than AI, if I'm allowed to say that. So we'll be looking at some classical questions in algorithms and data structures. This is joint work I did with Bernard Hoipler, who was a visiting master's student at Princeton some number of years ago, and I reconnected with him when he was at ETH in Zurich. He's also spending time in Sofia, Bulgaria. I worked with him and his grad students, undergrads, postdocs on this work. Classical algorithm, Dijkstra's algorithm, but it turns out until recently there were interesting questions to which we didn't know the answers. And that's what I want to talk with you today about. Now, let me first start. I think I've earned the right to make some general observations about computer science. You know, this is still a young discipline. Computer science has been around as a discipline since maybe the end of World War II, since the invention and construction of stored program digital computers. And we have developed the first computer science departments. Princeton only started its department in 1986 when I joined, but Purdue was the first one in the US in 1963, I think, but I have heard that Tony Melbourne claims the first computer science department in the world circa 1955. And I should thank Tony for this wonderful introduction. He was not my student, he was Moses Charakar's student, but I've always enjoyed interacting with Tony, and I'm kind of here because Tony joined you. So now, as I was saying, it's a beautiful problem-rich environment. Theoretical computer science is really a branch of mathematics, at least I think of it that way, but it's very young. Mathematics has been around for thousands of years. So there are plenty of open problems, and we theoreticians have often settled for the first good enough solution, sometimes striving for theoretical efficiency at the cost of simplicity, and maybe we haven't found the best possible solutions. Because the design space is rich, and it's only getting richer as computers become faster, memory sizes get bigger, we have to deal with multiple processors, and so on and so forth. All right, so my personal research goal has emerged to be to try to develop and analyze what I'll call reference algorithms. Paul Erdős was a famous mathematician and a great wit, had this concept of proofs from the book. Mathematical proofs from the book in the sky, God's book, best possible proofs. So since we're doing mathematics, why not think about designing algorithms from the book? As simple as possible, as efficient as possible, with provable resource bounds for important input classes, but efficient in practice. Make everything as simple as possible, but not simpler. The algorithm, the implementation has to be simple enough that coders are actually going to implement it and run it in practice. Although maybe with large language models, some of these complicated algorithms will get implemented, and then we won't have a clue as to whether they're implemented correctly or not. But now, another point I want to make is that data structures are very important. Any kind of combinatorial problem, the goal is to do some kind of computation. To do the computation, we need to understand what the data is and how we need to manipulate it. So Dijkstra's algorithm indeed is an example of this phenomenon where we're trying to do some computation on a graph, say a road network, and the algorithm, to get an efficient implementation, turns into a question of choosing the right data structure. What is the representation of the data associated with the problem that allows us to do the operations that we need to on the data efficiently to solve the problem? All right, so let's turn to this particular problem. Classic network optimization problem, the shortest path problem. And the version we'll look at is one source, non-negative arc lengths. So the Google map problem, or your favorite mapping service problem. I'm starting at home, I want to drive someplace. What's the fastest way to get there? Or what's the most gas or electricity efficient way to get there? Or what's the shortest path? That's the problem we want to solve. We'll solve it for the single starting point, fixed starting point, and all possible destinations. That's the single source problem. So by shortest, I mean the minimum sum of arc lengths, where the lengths can encode actual distances or travel times or fuel consumption, depending upon which measure you're interested in. And importantly, we're dealing with the directed graph problem because, for example, if you're driving into Sydney during morning rush hour, presumably it's a lot more slow going than if you're driving out of town during morning rush hour. Here's an example. S is the start vertex. We want shortest paths from S to all other vertices. So for example, we can get from S to D by several paths. If we go through A, it costs us 14, which is 5 plus 9. S to D via C, cost is 12, which is less. And if we go through F, we go S to C to F to D, the cost is even less, 10, and that is the minimum in this case. We allow cost 0. We do not allow negative cost. We allow cycles, but if the arc weights are non-negative, there's no point in repeating a vertex, because if you go around a cycle, you're just wasting fuel or time or whatever your measure is. All right. Now, Dijkstra's algorithm is in a famous short paper he published in about 1959. He actually was not the original inventor of this algorithm, but as is often the case, the person who invented the idea doesn't get the name. In any case, this is well known as Dijkstra's algorithm. And it's a very simple algorithm. It just uses the greedy method to find shortest paths. So the idea is we explore systematically from the starting vertex a distance at a time, in effect. So how does this work in detail? We'll maintain for each vertex in the graph the best length, the shortest length of a path found so far, and I'll denote that by d of v. So that's the length of the shortest path to v found so far. Initially, we're at s, so the distance to s is 0, distance from s to s. For every other vertex, the distance is initially infinity or some value that's big enough. All right, so what we're going to do is find paths and gradually reduce the distances until we get to the best possible set of distances. How do we do this? We maintain a set L, which we'll call labeled vertices. These are the vertices for which we found some paths, so we have a finite value of d of v, but we are not yet guaranteed that this is the best possible value. So the initial labeled set contains only the start vertex, because getting from S to itself, we pay 0, and we can't get there by paying less than 0. And all other vertices are not in the labeled set, yet. So here is the algorithm, very simple. While the labeled set is non-empty, we delete some vertex from the labeled set, some vertex with minimum current distance, d of v, and then we do what we'll call scanning the vertex v, which means we look at all the outgoing arcs and we see what kind of improvements we can get by using those arcs. So if I have a path from s to v plus another arc v to w, that gives me a path from s to v to w using the best path from s to v and the one more arc. The important property of this algorithm is because of the non-negativity of the edge lengths. When we delete a vertex with minimum current distance from the set L, we are guaranteed that that is the best possible value. So each vertex is only going to get deleted from the labeled set once, which is why this algorithm is efficient. Now let me finish the algorithm. We have to do the scan step here, which involves these updates. So we look at all the outgoing arcs from V for each such arc from V to W. If W is not yet labeled, we have found an initial path to W, which consists of the best path from S to V followed by the VW arc. That gives us a distance to W, which is the sum of the distance to V plus the length of the VW arc. So we set d of W equal to this value, and we add W to the labeled set. On the other hand, we may have found a better, if W is already labeled, if we already have some path to it, the path through V may be a better path, so we need to do an appropriate update. If the distance to V plus the length of the arc from V to W is less than the current distance to W, then we use the new path. We reduce the value of d of W to d of V plus c of VW. So what are the steps in the algorithm? We're adding vertices to the labeled set when we first discover a path to them. We're updating labels, and we're deleting vertices from the labeled set. Now let's go through at least the beginning of this example here. So initially, S is the only labeled vertex. It has a tentative distance 0. We delete it from the labeled set. We now know that its tentative distance is its actual distance, which is 0, and we scan it by looking at the two outgoing arcs. We get a tentative distance to A of 5, 0 plus 5, and to C of 6, 0 plus 6. So after the scan of X, S, here's the picture. A and C are the labeled vertices. S is done. And we pick A as the next vertex to scan because its label is smaller. It's 5 versus the 6 of C. So now we scan A. We look at the 14 arc and the 9 arc. We get a path to D, which has length 5 plus 9. So D goes in with an initial label of 14, and B goes in with an initial label of 19. And we're done with A. We know the shortest path to A. Now you will notice that I'm putting the vertices that we've scanned in blue and the arcs that give the shortest paths also in blue. This algorithm builds a tree of shortest paths as it discovers shortest path to the vertices. So it has this additional nice property. In any case, now we have B, C, and D in the labeled set, and C has the smallest distance. So we remove C from the labeled set and scan it, and now something new happens. Specifically, when we look at the CD arc, we get a cheaper path to D. So D is in the labeled set, but we now have a better path, so its value goes from 14 to 12, and we also get an initial path to F, which has length 10. So F goes in, D has its value reduced, B just sits there, and now this new vertex F has smallest distance, so it is the next vertex scanned. And now when we scan F, G is going to go in as a new vertex, but we get yet a smaller distance to D because we now have this 3-hop path to D, which has cost less than either of the previous 2 paths, and so on. So if you took an undergraduate data structures or algorithms course, you will have seen this algorithm. So again, this goes back 65 years, roughly. It's relatively easy to prove that it's correct. The important property is that when you remove a vertex, its current distance is minimum. Importantly, vertices are scanned in non-decreasing order by distance from S. So you get some extra properties from this algorithm. You get the set of vertices scanned in the order of the distances from S, ignoring ties, which means that you could stop early if, for example, you're starting with some given amount of fuel from home and you want to see what places can I get to, and then you're going to pick one to go to. This might be an issue with an electric car, for example. So we get this extra property. That is, Dijkstra's algorithm not only computes shortest distances, it solves the distance order problem. It sorts the vertices in order by distance from S. And it also builds a shortest path tree rooted at S. So it builds a tree which instantiates shortest paths. It's a compact representation of shortest paths from S to all vertices reachable from S. Now let's look at efficiency. This is where we go from a graph problem to a data structure problem. So this algorithm runs this simple loop. What happens inside the loop? We delete some vertex from the labeled set, but we delete one which has minimum tentative distance. The key here is we have to maintain the labeled set. Every vertex in this set has a non-negative real value, which is its current distance. We need to be able to delete the min. That's one operation on L we have to do. Then we have to do the operations that arise in the scan, and there are 2 kinds of operations. One is insertions of vertices for which we find an initial path. If W is unlabeled and we find any path to it, we add it to the labeled set. That's an insertion. And if we have a vertex that is already labeled, but we find a shorter path, we have to update its label. I'm going to call that a decrease key operation. That is, the algorithm is essentially doing a sequence of delete min, insertions, and decrease keys on this labeled set, which initially contains a single vertex, the start vertex. And the rest of the overhead is just inspecting the graph, which is, we have to look at all the graph vertices and arcs to solve the problem, so I'm going to ignore that part of the work and concentrate on the data structure here. More specifically, if we have n vertices in our graph and m arcs in our graph, then Dijkstra's algorithm takes linear time, order n plus m time, plus the time for the data structure operations. The n at most inserts into L. Every vertex goes in once, comes out once. So there are at most n insertions, at most n delete mins, and at most m, actually m minus n plus 1, decrease key operations. So a typical graph, the number of arcs is larger, conceivably much larger than the number of vertices. We're interested in the running time as a function of the number of vertices and the number of arcs. If you think about road networks, current kinds of applications of shortest path algorithms, the graph is very sparse. The number of road networks, the number of road segments is linear or only slightly superlinear in the number of road intersections. So you can think of m as being more or less proportional to n for interesting large applications, which is what these sorts of algorithms are designed to handle. Now, what we need to finish the job for the implementation is we need to implement the L set. We need a data structure that efficiently supports insertions and delete mins and decrease key operations on a set that is initially empty or contains a signal element, and each element has some real valued key. Such a data structure is called a heap. I call it a heap, or some people call it a priority queue. So if we have an efficient data structure that can do the three kinds of operations, then we get an efficient implementation of Dijkstra's algorithm. Now, Dijkstra in his original paper ignored the data structure question. His data structure is sort of the obvious one, just an array of that contains the values of the keys indexed by the vertices. So you can think of the vertices as being numbered 0 to n minus 1 or 1 through n, and each slot in the array contains the current distance of the vertex. That makes insert and decrease key constant time because you just go to the right slot and change the value. But the delete min, you have to scan the entire array to find a minimum. So delete min is the expensive operation. Order n time, where again, n is the number of vertices. So when you add the time up, you've got the time is dominated by the time for the delete mins, which is order n squared. Now, if you have a graph that is dense, that is most possible edges are present, this is best possible. So in some sense, Dijkstra's original algorithm as implemented, you could say is optimal, but only on very dense graphs. On the other hand, if you want to run Dijkstra's algorithm on a sparse graph, this is a terrible implementation because it's quadratic in the number of arcs if the number of arcs is proportional to the number of vertices. Williams, this is 5 years later, building on work of Bob Floyd, who was my thesis advisor at Stanford, invented what is actually called the heap data structure. It's a binary tree that's implemented in an array, and the vertices are heap ordered, which means that if we have a tree, the root contains an item of minimum key, so you can do the find min very fast. And the effect for our purposes is to reduce the time per delete min to log time, because you have to do some updates when you delete the minimum, at the cost of increasing the time for insertions and decrease keys also to log time. So the dominant operation with this implementation of the heap is you have to do all these decrease keys, and the total time is m, the number of arcs, times log n, which is the data structure overhead, times some constant factor. And this implementation, or some variant of it, is currently still, I think, regarded as the best in practice, but not a binary tree, a degree 4 heap ordered tree. The reason this is efficient in practice is because it's so simple. You can store it in an array, so you can use array addressing. No pointers for those of you who like list processing. But maybe not best possible theoretically. Now, this is a question that Mike Fredman and I looked at 20 years later, 20 plus years later. We asked the question, well, the important operation here, the frequent operation, is the decreased key operation. If we could reduce the time for decreased key operations, say to constant, and have the expensive operations, the delete mins, be the only ones that take log time, then we would get a better bound. We managed to invent a kind of heap implementation, which we call the Fibonacci heap, because the Fibonacci numbers correspond to the worst case in this data structure. It's a pointer-based data structure, and it does indeed have a time per decreased key, which is constant, and a time per insert, which is constant, and a time per delete min, which is log n. These bounds are in the amortized sense, not the worst case sense. What does that mean? We're interested in a long sequence of operations. So we don't care about the time of the individual operations. We only care about the total time. So we're willing to allow individual expensive operations if we have lots of cheap operations. So the property of this data structure is that the sum of the times for any sequence of operations is constant per insert plus constant per decreased key plus log of the current heap size per delete min. And that allows us to get a bound on Dijkstra's algorithm, which is linear in the number of arcs plus this n log n overhead. So this bound is optimum for any graph that's sufficiently dense. That is, if the average number of arcs per vertex is logarithmic, then the n log n overhead gets absorbed in the linear order m term. So that's kind of the classic or semi-classic history. So this was invented before most of you in the room were born. But I'm still working on these problems, as we'll see. And there are still interesting open questions. Now, what about optimality? Can we do better, or in what circumstances can we do better? Well, in the worst case, we have to look at every arc in the problem graph. So we got to spend linear time in the number of arcs. And that tells us that Dijkstra's original implementation is optimal on dense graphs. Furthermore, there's a sorting problem built in here, provided that we're trying to solve the distance order problem. So let me remind you that Dijkstra's algorithm not only computes shortest paths, but it produces an order of the vertices sorted by distance. So I want to focus for the moment on the distance order problem. The problem is produce the vertices in sorted order by distance. So we have to do a sorting problem on n vertices, and that says that for the right kind of graph, you have to spend n log n time. And that means that this bound that comes from Fibonacci heaps, m plus n log n, is best possible, at least for certain graphs, for the distance order problem, assuming the classical lower bound for sorting, which is n log n to sort n items, which assumes that we're doing binary comparisons of sums of arc lengths, which is what Dijkstra's algorithm does, and which many of the classical algorithms do. And let's assume that we're going to make this restriction. We're going to compute shortest paths, solve the distance order problem by doing binary comparisons of sums of arc lengths. All right, now this is for certain specific worst case graphs, but suppose I'm working with only certain kinds of graphs, like road networks have some particular structure. They're almost planar, except for bridges and tunnels. And they also have a hierarchical structure because you have superhighways and then semi-superhighways and local roads and so on. And you can take advantage of this structure, and indeed, current shortest path algorithms that are built into these apps use the structure. So what if the graph structure is known in advance? Specifically, suppose I give you the graph, but I don't tell you what the arc lengths are. Can you design an algorithm for the particular graph that minimizes the total time and the number of comparisons, an algorithm that is specific to the graph, customized algorithm? I want to look at optimality in a more refined setting, kind of an instance per instance setting. So for any particular graph, there's some kind of optimal algorithm. We don't know what it is. It might be complicated, but is there an algorithm, a general purpose algorithm that in fact works as well on every graph as the best possible customized algorithm for that graph? That's the problem I want to address now. And this is philosophically a lot of what's going on these days in algorithm development, going beyond the worst case, trying to look at taking advantage of the specifics of the inputs that the algorithm is going to have to deal with. So my co-authors coined this term, which is a little highfalutin for this idea here. We'll call this universal optimality. So the specific question is there an algorithm that minimizes the running time and the number of comparisons to within constant factors on every graph as compared to the optimal customized algorithm for the given graph? And it turns out our answer is that for the distance order problem, where you have to produce the vertices in order by distance, the answer is yes. And indeed, there's an extension of Dijkstra's algorithm that uses the right kind of heap implementation that gives us this general purpose algorithm that cannot be beat even if you know the graph but not the arc lengths in advance. So you can design your own custom algorithm for the particular graph structure. Now, to illustrate why this question might be interesting, let's consider this example, which consists of a long path and some smaller number of vertices that have direct paths from the start vertex. So the one vertex at the left-hand end of the screen on the top, this is the start vertex. So we can get from the start vertex, we can walk along this long path. We can also get to all the individual vertices. This is a tree. There's only one path from the start vertex to any other vertex. So this problem is trivial, at least the problem of computing the lengths of the shortest paths, because we just walk along the long path, adding up the arc lengths, and we've only got a direct path to all the other vertices, so that's easy to compute. On the other hand, if we want to produce the vertices in sorted order by distance, things are a bit more interesting. So how do we solve the distance order problem? Let's back up a bit. Let's think about Dijkstra's algorithm with some kind of heap implementation. So we scan the start vertex. The set of vertices that go into the heap are those one step away from the start vertex, of which there are k vertices. The ones on the bottom here plus the second one on the long path. So after the scan of the start vertex, there are k vertices in the heap. And it doesn't matter whether we use a Fibonacci heap or some other heap implementation. Let's suppose that now the next smallest distance is the one for the vertex on the long path. So the sum of the lengths of everything on the long path, all these arcs on the long path, suppose that's less than the length of all these single arcs of the vertices on the bottom here. Then what's going to happen at each step of Dijkstra's algorithm is we're going to remove one vertex from the long path, put in the next vertex on the long path, and keep going until all the vertices on the long path, we know their shortest path length. And then we're going to delete all the remaining vertices, which are the ones on the bottom. So each time we do an insertion, the following delete min, the size of the heap is going to be k. Size of the heap after the first vertex is scanned is k, and it just stays k until near the end. So the standard, any implementation, Dijkstra with a Fibonacci heap or any other kind of heap, is going to give something like m log k, which is n log k, because again, this graph is sparse. The number of arcs is proportional to the number of vertices. So think of k as being square root of n. Then log of square root of n is a half log n, so we're spending n log n time. On the other hand, the only sorting we have to do here, in fact, is we have to sort the vertices on the bottom by the length of the arcs connecting them. And then we have to somehow insert those distances into the distances corresponding to this long path. Now that's in fact a merging problem. So you can compute shortest paths on this graph by sorting the arc lengths for the bottom set of vertices. That takes k log k time. Then you get one sorted list. Then you get another sorted list for free with no comparisons. And then you have to merge the two sorted lists. Now, those of you who remember your sorting and merging algorithms will remember that merging two sorted lists takes time linear in the total length of the two lists. So if we do that, that gives us a customized algorithm for this particular graph that will solve the distance order problem in m plus k log k, which is the minimum possible time here, because we have to do this sorting, but only of a relatively small set of vertices. And if k is something like the square root of n, as I said before, the running time is linear in n, but Dijkstra with the Fibonacci heap takes the extra factor of log n, which is not necessary. So now the question is, can we improve things on examples like this? That's the question we want to try to address. I just said this. All right. This is kind of the key observation here. If we go back to this picture, the bad situation with Dijkstra's algorithm of the classical heap is that each of these vertices on the path, if the total path length is short, we're removing one from the heap and inserting the next one on the heap, and this is happening repeatedly. And all these vertices in the bottom are just sitting there, getting in the way. They're costing time in the bound on the data structure, but somehow we shouldn't have to pay for this. And the question is, can we avoid paying for these old vertices if they're not affecting what's going on? Can we prioritize new vertices that go into the heap more recently than other vertices? That's the suggestion here. So that's the key to trying to do something better. This observation. So here's a possible approach to this question, a positive approach, rather than proving that it's not possible. If it were not possible, this talk would be less interesting. So we need a heap implementation that gives preference to recently inserted items. At least that's the conjecture. So let's quantify what this means. Let's define the working set of an item. So an item goes into the heap, it sits for a while, it comes out of the heap. There are items that were inserted into the heap before it went into the heap. Those are the old ones. The items I'm interested in are the ones that are inserted into the heap between the time it was inserted and the time it was deleted. I'm going to call that set of items the working set. And the working set size is the number of those items, the number of items that go into the heap at or after the time X was inserted and are inserted before X is deleted. So that we're looking at insertion time, not deletion time. These items may still be in the heap when X is deleted, or we may have deleted them. It doesn't matter. They still get counted. The important thing is they were inserted after X was inserted, but before X was deleted. So we'll say a heap has the working set bound if the time per insertion is constant, the time per decrease key operation is constant, and the time per delete min that deletes an item X is log of the working set size. Now the working set size can be either bigger or smaller than the size of the heap when X is actually deleted. Turns out it doesn't matter. This is just the definition. So this is a little bit of a funny notion. This is actually simplified from a more complicated definition, but the important thing about it is if a heap has this working set bound, it gives priority to recently inserted items. When you want to delete an item, you're only paying log of the number of items that were inserted after it was inserted, and the ones in the beginning don't count. So in particular, if we had a heap with the working set bound, and we run Dijkstra's algorithm on this graph, this insertion deletion process, the working set size of all the vertices on the long path turns out only to be constant. So the only vertices that have a large working set are the ones that are one step away from the starting vertex. So if we had a heap with the working set bound, we plug it into Dijkstra's algorithm, we would in fact get a running time that matches the lower bound versus what at least the Fibonacci heap bound would give us immediately. So you saw my answers. Here are the two questions. The first one is Dijkstra's algorithm using a heap with the working set bound universally optimal? That is this the right property, or is this a sufficient property to guarantee that this general purpose algorithm runs as fast as any algorithm customized for the specific graph that we are presented with? So again, the graph is given to us. We don't know the arc lengths. If the answer is yes, we can then ask the question, well, is this too much to hope for, or is there some kind of a heap implementation that has the working set bound? And again, I wouldn't be here speaking on this topic if the answer to both questions were not yes. All right, so let's take a look here. So the claim is that on any graph, Dijkstra's algorithm using a heap with the working set bound is universally optimal in running time, and it's with an, so what I said is not quite true, but we'll get to the not quite part. If we're just counting comparisons, not just total running time, there's an extra linear term. So if I go back to my example here, if you use a working set, you got to pay constant number of comparisons for each insertion, which means that you got to pay for the long path. But in terms of comparisons, there are no comparisons for the long path. The number of comparisons you need on this problem is just to disambiguate. That's actually not true. You have to sort the vertices on the bottom, and then you have to do this merge step. But the time to do the merge, if you're clever about it, can be sublinear in n. So you don't need, there's an extra additive n term if you just use a heap with the working set bound, which is not happy for a theoretician, but that's a secondary phenomenon, and we'll deal with it in a minute. All right. Right. So in terms of time, we have to look at all the graphs. So the additive O of n in vertices is irrelevant. If we really care about comparisons, there are examples like my canonical example so far where the number of comparisons is actually sublinear in n. So if you really want to count comparisons, you want to get rid of the additive linear term. Now let me outline the proof of this. The proof is interesting. I'm not going to go into the details, but let's just think about how this might work here. There's a sorting problem. Those of you who remember your data structures course, I hope, saw the lower bound for comparison-based sorting. If you want to sort n numbers, you have to pick the right permutation. There are n factorial permutations of n numbers. That's n factorial different possible outputs that your algorithm has to choose one of. If you're doing binary comparisons, you start out with n factorial permutations. Each comparison splits the set of possibilities into two buckets. If you're the adversary, you say the answer goes one way to give me the bigger bucket. So every comparison only halves the number of possibilities. You have to go from n factorial down to 1 by dividing by 2. Number of comparisons you need, therefore, is log of n factorial, which is proportional to n log n. So to sort n numbers, you need n log n binary comparisons. Here we're trying to find a distance order. So there's a lower bound in comparisons, which is log of the number of possible distance orders. What do we mean by a distance order? This is an order of the vertices that corresponds to some choice of arc lengths for our particular graph, where the distance order is the same as the shortest path length order. Now here's a related concept. I'll call an order, given a directed graph, which is what we know about the input, we don't know the arc lengths, with a source vertex. We'll say a search order is a total order of the vertices such that S is ordered first, and if we have any vertex other than S, there has to be an incoming arc from a previous vertex in the order. I'm calling this a search order because if you start out from S, and you take a step at a time, and you're only allowed to take a step from a vertex that you've seen before, and you generate all possible vertex orders by doing that, you will get all possible search orders. Now the claim is, the first claim, I've stated as a lemma here, a vertex order is a search order that's purely a property of the graph if and only if it's a distance order for some set of non-negative arc lengths. That's fairly straightforward. You just construct for any search order the right arc lengths, and then you get a corresponding distance order and vice versa. Second result is that if you have an algorithm that generates the vertices in distance order, the number of comparisons it has to do is proportional to log of the number of possible distance orders. So you got to do log D, where D is the number of distance orders, which is the same as the number of search orders, comparisons. That's just the sorting lower bound applied here. So these two things are straightforward to prove. Now here's the interesting result, which is that if you look at any run of Dijkstra's algorithm for any set of arc lengths, and you sum the logs of the working set sizes, then that's at most a constant factor, small constant factor, 2 actually, times the log of the distance, the number of distance orders of that particular graph, the number of search orders of that particular graph. So that means that if you have a heap with the working set property, the insertion state constant time, the decreased key state constant time, the delete min time is the sum of the logs of the working set sizes, which is what's on the left-hand side of this equality. And on the right-hand side is log of the number of search orders, and we have to do that many comparisons. So we're optimum in comparisons to within this additive O of n term, which actually comes from the number of insertions that we have to do. Our original proof in the original journal conference version of this paper, I encourage you to think about how you might prove this. I'll give you the reference at the end. this is an interesting mathematical result, and there's a beautiful lemma which is implicit in this paper by Cardinal Fiorini, Jungers, and Ian Monroe in 2010. It was reformulated in a way that makes it more directly applicable to this problem by van der Hoog, Rodenberg, and Rishman very recently, 2024. So, given this proof, this basically gives us the result that we wanted. An any-graph Dijkstra's algorithm using a heap with the working set bound is universally optimal in running time and within a additive linear and vertices term in comparisons. And again, the additive linear term essentially comes from the insertions, although it's also based in, it has to do with the difference between the log of n to the n and log of n factorial. There's a linear term there also. Technicalities, which always creep in, which every talk ignores. So we did part one. Part two is, is there a heap that has the working set bound? Because if we can't design one, or if this is too strong a property, the previous result is useless to us. Now, here's an interesting fact. There is a self-adjusting kind of heap structure that I also invented with a group of colleagues mid-1980s called the pairing heap, which was intended to be a self-adjusting version of a Fibonacci heap. Fibonacci heaps are efficient in theory, but they're a little complicated to implement in practice, and we wanted something simpler. They're not quite as good as Fibonacci heaps because the decreased key operations are not constant time. But if there are no decreased key operations, then it turns out that insertions are constant time. And furthermore, John Iacono, 15 years after we invented the data structure, proved that this heap has the working set bound provided that it ends empty, which doesn't matter to us because everything that goes into the heap is eventually removed. Turns out you can get rid of the requirement that the heap ends empty by modifying the data structure a little bit. So this almost does it for us and gives us a hint that it's possible, but we have to handle decreased key operations. The most interesting thing about this result is that, so this was 25 years ago. John Iacono was a student of Mike Fredman, who was interested in data structure properties and so on. He invented this result. He came up with a description of the working set property and proved this bound, but he had absolutely no applications for it. So this is the first application I know of this concept of the working set bound in the heap context. A similar idea occurs much more naturally when you think about binary search trees, and that's a topic for another talk. In any case, this suggests we can do something here, except we have to handle the decreased key operations. So rather than using this previous data structure, we had to invent our own because we have to implement decreased key operations in constant time. So our solution is to build on top of the Fibonacci heap, which does have the property that decreased key operations take constant time. And instead of using one Fibonacci heap, we use a collection of Fibonacci heaps. So we have here's the picture. So this is our overall heap structure. It's a list, and each one of these triangles denotes a Fibonacci heap, which we're treating as a black box. And they're exponentially increasing in size, actually doubly exponentially increasing in size. So if we have k elements total in the heap structure, there are only log k of these triangles, and the last one, the biggest one, has by far most of the elements in it. But the property is the working set bound, we want to favor recently inserted items. So the very first heap, the one on the left, has the most recently inserted items. Those are the items inserted, those items are inserted after all the items in the next one to its right, all of which were inserted after the ones in the next one to its right, and so on. So the oldest ones are in the big heap, and the more recent ones are in the next smaller heap, and so on. The point is that if we're going to delete something in the big heap, there are all these earlier items, leftward items, that were inserted more recently, and we are willing to pay, what is the working set size of this one? We're willing to pay log of the total size of all of those heaps in order to do a delete min out of here. So if you play with the numbers, it turns out you get the working set property as long as these things increase at most a double exponential rate. So that's the idea. Now, there are technicalities in getting the details to work here. In particular, when the one on the left, it's getting bigger as I'm doing insertions, because the insertions are always on the left. When this thing gets too big, we're going to meld it, that is, combine it with the one to its right. And when that one gets too big, we're going to combine it with the one to its right, and so on. So we have to be able to do these meld operations. Unfortunately, Fibonacci heaps support combinations like that in constant time, so that's not an issue. But we have to keep track for each element of which one of these heaps it's actually in. And that, it turns out, that's the first problem here. There's another problem, which is that we got a double log number of individual heaps, so where is the minimum? It's the minimum of one of these, and we have to figure out which one it is. So we have to build some kind of inner heap on top of these local minima. So that gives us two additional subproblems we have to solve. The first one, keeping track of where everything is another classic data structure problem called the union find or disjoint set union problem, which is another topic that I'm not going to go into. Turns out to be a special case that we can solve in constant time, so that problem goes away. The problem of keeping track of the minimum among the inner heap minima, that's a little more complicated, but we have a solution for that too, which is also constant time per min. And it relies on the fact that the number of heaps is doubly logarithmic in the total number of elements. So we do some array tricks to get that to work. That's the part we're all least satisfied with. You can also use recursion, and if you do that, you might get an extra, I hate to say it, a log star overhead here, which would be unfortunate, at least with arithmetic. Okay, I'll refer you to the paper for all the details. I'm over time already. I will just say that we can get rid of this additive term in comparisons. The issue has to do with long paths. And we can get rid of this by chopping the graph up. If we look at this graph, this vertex G, for example, all paths to H and T have to go through G. If we find what I'll call bottleneck vertices, which are vertices that cut off one piece of the graph from the rest of it, and chop the graph up into pieces using the bottlenecks, we can run Dijkstra in a recursive fashion, where when we scan a bottleneck, we do a restart, we do a recursive call of Dijkstra itself and proceed in that way. And that allows us to get rid of this additive end term in terms of the computation. So here's the picture. We end up with a set of bottlenecks that are sitting on some long path, V1, V2, V3. We start our Dijkstra at vertex S. We've pre-computed all the bottlenecks, which takes linear time. When we scan the first bottleneck, V1, we start a new Dijkstra computation with its own heap. And it explores some piece of the graph denoted by this second triangle down here. When we get to the next bottleneck, V2, we call a new Dijkstra, and so on and so forth. The last bottleneck in this picture is V3. When we finish with the V3 search, we back up to the V2 search, finish that one, and so on and so forth. In the picture, we can have arcs that go from an inner problem to an outer problem. Those correspond to decreased key operations in the outer problem. We do those using decreased key updates, constant time. They're not a problem. This produces the correct distances when we go through the whole recursion. We still have the problem that things can end up being out of order. So there's an additional data structure we need to plug in here to actually get the vertices in increasing order by distance. So that's the summary, and here's the reference. The Fox version of the paper is much more complicated than what I've attempted to describe to you here. I did a complete rewrite on this paper for the journal version, which is now, you can find it on arXiv. So I refer you to the arXiv version for the nice version of these results. This is also one of my pet peeves. You know, computer science, everybody publishes in conferences and nobody publishes in journals, which means there's a lot of half-baked stuff in conferences that could be written up in a much nicer way, and I wish people would take the time to do this. Publish less, clean up your work, put it in journals. This is an unpopular point of view because there's this publish and perish cycle, right? But you know, in the long run, we want these things to live on, maybe beyond us, if that's possible. So, okay, so that's an answer to yes to this question, is Dijkstra's algorithm optimal? But that's for this distance order problem. Now, what if we only want the distances? What if we don't require them in sorted order? Well, there's this amazing new result which shows that Dijkstra's algorithm and related algorithms are not, in fact, optimal. If you only want the distances, you can compute correct shortest path distances and a shortest path tree in m times log to the 2/3 power of n time. That's a very recent result published in Stock. There's a symposium on theory of computing 2025, which was this past June. So this is a real breakthrough result. So the answer is you can have it either way, defined depending upon which version of the problem you're trying to solve. And this is there any reason to believe that you need to spend log to the 2/3 n time? No, this can't possibly be right. So this result is going to see some improvement here, I think, eventually. Good. Let me say just one more thing. There's this sorting problem. That's what we're really dealing with. Well, there's a even simpler sorting problem that's a classic one, which is sorting using partial information. So as I said, you need n log n time to sort n numbers, assuming you know nothing about the order ahead of time. Suppose I hand you some comparisons that I've already done. So this number is less than this number is less than this number, and so on. That's the sorting using partial information problem. Is there an algorithm that will sort using a number of comparisons that's minimum possible given the pre-existing comparison outcomes? This is a classic problem that I don't have time to talk about. It turns out that it's really the same as the Dijkstra optimality problem that we worked on, minus the sums of arc lengths. John Iacono is the one who pointed this out to us. So we've got a corresponding result that gives an optimum algorithm for this sorting problem using partial information. And this is kind of the culmination of a long sequence of papers that gave optimal bounds in terms of comparisons, but the running time of the algorithms were high, and the algorithms are very complicated. Here we get a simple natural algorithm, and here we can use the existing pairing heap data structure to get the result, because there are no decreased key operations. So that paper is in SOTA this past year. It just got accepted to Algorithmica, so the journal version will be out relatively soon, I think. In any case, again, this paper is on arXiv. I refer you to either version. The arXiv version is more or less the same as the SOTA version, I think, in this case. And I'm sorry to have kept you so long, but thank you very much.